Flipped classroom video for Maths A2 Unit 3 Pure. This is M2.3.7A2 and it deals with the integration of exponential functions. So we know already that the differential of e to the x is e to the x, where e is Euler's constant 2.71828, etc. It looks as if it's going to actually recur, but it doesn't. It is an irrational number, and the reason for that is the gradient of e to the x is 1 at 0, 1, and if you refer back to your first principles differentiation, or your differentiation which was in M2.3.6c4, then the property of any exponential function is that it's going to be the exponential function multiplied by its gradient at 0, 1, and because the gradient of e to the x is 1, you'll get 1 times e to the x, which of course is e to the x. And we also know that e to some function in x is given by f dashed x e to the fx by the chain rule. Yeah, okay, you can actually consider it using other aspects. So it follows straightforward that the integral of e to the x with respect to x is e to the x plus a constant, and you've heard me drone on about it before. Never ever forget the constant of integration. It will cost you marks, and the more marks you throw away, the harder it is to get the top grades. The integration of e to some function x is relatively easy if fx is a linear function, because the differential of a linear function is just a constant. And what I would tend to do when I'm dealing with integration of e to some function x, where it's not just x on its own, then I would always be tempted to differentiate the function in x, because it will then tell me what sort of thing I'm going to get. So if I consider e to the ax, where a is any constant I choose it to be, so in this particular case my function in x is ax, so therefore f of x is equal to ax, and it's actually a double implication, because if f dashed x is equal to a, then it does rather imply that fx will be equal to ax, but not in every case. Remember that constant. Okay, so it is a single implication here. F of x is equal to ax, f dashed x will be equal to a. We're not going to labour that too much at the moment. So therefore, by definition, the integral of a e to the ax would have to be e to the ax plus a constant. But if I've only got e to the ax with respect to x, and use the same trick as I did before, I treat that as 1 times e to the ax, then I can treat my 1 as a over a. I can whip the 1 over a out the front there. Therefore, I've now got the integral of a e to the ax with respect to x, which is e to the ax plus a constant. So therefore, I'm going to get 1 over a e to the ax plus k. And 1 over a times a constant is still a constant, so don't worry faffing around distributing that 1 over a across it. It works quite happily. Now, if I went to a general linear function, anything of the form ax plus b, then remembering your laws of powers, you will realize that in this particular case, the f of x is equal to ax plus b. Therefore, f dashed x is equal to a again. Now, e of ax plus b is the same as writing e of ax times e of b, and e of e to some constant is another constant. Therefore, I could actually whip that outside the integration and treat it as e to the b integral e to the ax with respect to x, and we already know that the integral of ax with respect to x is 1 over a e to the ax plus a constant. So therefore, nice and easy, I'll get e to the b over a e to the ax plus some constant. And I guess I don't really need those brackets in there, but I've put them in there anyway. Now, what happens if I've got nonlinear functions? Because it could be something a bit more wicked, and it could even be e to the sine x or e to the cos x, but you won't get those as absolutes. You'll get something quite interesting going on. Now, it's important that we remember that e to some function in x, the differential of that is the differential of the function times e to the function in x. That function x doesn't change as a power ever. So the questions that you're going to meet, if they're nonlinear functions, will always be of the form some function in x multiplied by e to some different function x, but it's a related function. Now g of x will be a multiple of f dashed x. So if you consider here, where I've got written the integral of 6x e to the x squared with respect to x, and it's a case of recognizing that the actual outside of this, the first part of it, the 6x, the bit outside to the left of the bracket, is a multiple of the differential of x squared, and that's the giveaway. So you will always expect them to be this way. If my f of x is equal to x squared, then my f dashed x would be equal to 2x. And you can see straight away, because you're bright, intelligent young human beings, that my 6x is actually 3 times that. So I could rewrite, if I choose to do so, my 6x e to the x squared with respect to x as 3 times 2x e to the x squared with respect to x, which means, again, I can pull that 3 out the front to make my integration easier. And what I've got now is 3 times the integral of 2x e to the x squared, which is a straightforward integration. The bit outside the bracket is the differential of the bit inside, therefore it will become straight away e to the x squared plus a constant. So I've got, in this particular case, 3e to the x squared plus some constant. So you'd expect to see anything of this format that I've got here, some function in x e to some related function in x, and it's related by a differential calculus, and that's the thing you've got to get into the habit of spotting.